Hello everyone, welcome to our presentation. Team GeotherML is going to talk about the approach we gave to this geothermal data that came from Utah Forge project. The agenda is the following one. We will introduce ourselves, then we'll talk about the exploratory data analysis, data modeling, code overview, evaluation metrics, way forward. Then we have a section of final comments. My name is Antonio Dagnino Mendez, member of GeotherML team. The participants are Andres Calvo, Oliver Rojas, Yusuf Falola, and Chandril Paterne. As you might know, the project scope is to seek the theoretical optimum placement of the production well that maximizes the net energy and electrical power output over a 20-year lifespan, accounting for parasitic losses. Moving on exploratory data analysis, we could mention the following. We imported libraries like NumPy, Matplotlib, Pandas, Scikit-learn, and even Seaborn. We dealt with missing data, we checked for columns without meaningful information, and we will explain more in depth shortly. We defined inputs and outputs based on project scope. We checked for correlation between features. We average time series to yearly time series. We merged data sets. We concatenated data frames. And this is overall what we did in terms of exploratory data analysis. Regarding checking and filtering inputs without meaningful information, we looked for features that have only one unique value across all datasets. Those two variables will not contribute to the neural network. Instead, it could cause noise and slow training feeding down. Here, it's important to mention that some well-designed variables like azimuth, depth, and count had the same value, and we do consider they are important for machine learning algorithms to understand better the outputs. We did not use these inputs for the model, but we'll leave that comment on a side to move on. Besides filtering some inputs, we did some feature engineering to embedded time series variables. In other words, we changed time frequency of enthalpy, power output, and thermal power to yearly frequency. This allowed better data handling and fit the model with 20-year data, so it could replicate that format based on the project scope. In other words, we want the model to predict 20-year lifespan, so we trained the model with 20 years of data. The data was split based on instructions from the organizer of the project and the project scope itself. We merged data from two datasets to increase amount of data being used and seek for better evaluation metrics. After exploring data and applying feature engineering, we modeled the data the following way. 3 separate neural networks were created to predict time series outputs, including time series of HPRO, PHOUT, and DHOUT for 20 years. Based on the project scope, we used 37 inputs, and each neural network made 20-year predictions, one for enthalpy, one for power, and one for thermal power. To give some insights about the model and code overview, we applied 80-20 train test split, then train data was scaled before feeding the neural network. The neural network had 5 layers, included input and output layers. 37 neurons per layer except the output layer, which had 20 neurons, where each one will predict 1 year of the output. The model was fitted with 400 epochs and 128 for batch size. To make sure the model was created with best combination of hyperparameters, layers, and neurons, we use early stopping method to avoid overfitting, and dropout function, which drops unnecessary neurons. The batch size and epochs are easy to tune since they were instantiated. And finally, the losses were monitored by doing a loss value plot, like the one you can see here in the slide. After running the neural network, initial evaluation metrics were obtained. These metrics were obtained per neural network and per every single year predicted. So regarding enthalpy, mean absolute error was with a range from 58 to 71 year on year, and MSE from 8,000 to 12,000, and RMSE from 89 to 110. R2 score and explain variance score about 75%. Then thermal power had little lower explain variance scores and R2 scores average. And finally, power output with the lowest explain variance score of the model. After obtaining these results, we think we could definitely improve these results with further analysis and a way forward. This is power output right here. As you can see here, all the evaluation metrics that we made for. The way forward is to improve all these models. We could optimize the high parameters using a library called Optuna. That library would use a combination of hyperparameters and seek for the best network to improve all evaluation metrics so far. Then another action that could be taken is to improve input data features like azimuth, deep, length, count. If, as we mentioned before, if we had the behavior of the outputs with variance in these inputs, we will definitely improve the model. Another action will be use yearly data to retrain the neural network, just like a recurrent neural network like model, just to retrain the model based on the last year you have to predict a new year, and then implement other networks for the rest of the outputs of the database. So thank you for the opportunity. Thank you for your time. I hope you have liked the presentation, and please reach out if you have further comments, suggestions for us. It was a great opportunity to learn about geothermal, and looking forward to work with you again. Follow me on GitHub and write us if you have more comments. Thank you.